You just go over to the right a little more and you'll be fine. You don't have to panic. Good evening, Pittsburgh and universe. This is JC on a bike. My name is JC, and this is Journal Club on a bike. It's a brief shout out today. It's 60 degrees on the way home on November 26th. It's a little cool, but by the time I get moving, I don't think it's going to be cool at all. I lost a glove today at work, which is annoying. And I'm going to do a brief shout out, which I think I deleted on accident last week. And it's a shout out to MIT and to the lab of Mark Harnett, whose PhD or postdoc Jakob Voigt has made a little bit of a methodological advance and a little bit of a scientific discovery all balled up into one neuron paper. So there has been this question, long-standing question about dendritic computation, and all the dendritic people are convinced that dendrites do things on their own. Even when the first backpropagating action potentials were done in Bert Sackman's lab, the implications were already obvious that if these compartments are electrically active on their own, then it follows that this apical dendrite may indeed be a separate computational unit. And if it is, the question would be, how would we come about that? How would that come about? And how would we experimentally test that? And so there are lots of potentially clever ways to do it, but what you really need is to be able to record from or image from the soma and the dendrite at the same time. And of course people can do that. People have done that now for a while in virtual reality on a ball. I'll try and throw in a video here on that. But there's a couple problems, but of course it's beautiful. You can do all kinds of things if you can image, if you can put a microscope on the top of an animal's head and then have that animal do something useful in terms of navigation or exploration. But the problem is, and this is the limitation of many of these virtual reality setups, is that the animal is still navigating in virtual reality. They're still running on a ball, and all of the landmarks in their environment, the landmarks are baloney, right? The landmarks are just things on the screen. They can never run into any landmarks. Landmarks can never have smell. The landmarks in virtual reality are just not landmarks, right? They're stripes on the wall or other rather nondescript, completely multi-sensory inputs. Whereas any normal obstacle, any normal landmark is going to be a multi-sensory input that you can see, you can feel, maybe you can even smell or see or hear. So that's a big difference. And so virtual reality can do lots of things. I don't know where he's going, so I'm just going. It's like he's not going, but he's going, so I'm going. So virtual reality is cool, but virtual reality still lacks one very big thing, and that is that direction. So where is the animal looking in the environment is no longer an option anymore. The animal has to buy into the virtual reality. And I think that's been a limitation for a very long time. Have we done stuff with virtual reality? Sure we have. And have we gotten data from mice in virtual reality? Sure we have. But is this data real relative to what the brain in the mouse or the rat really does? We don't really know. We really don't. Because a lot of the cells in the hippocampus and the hippocampal system proper, like medial entorhinal, these cells don't behave like they do in the open field in virtual reality. They just don't. Number one, because virtual reality is a limiting factor. It's oftentimes just a linear maze, virtual linear maze. And even if it's a virtual open field without enough virtual landmarks is really nothing. So that's a lot of the reason why they've used these two-dimensional mazes in virtual reality, because at least then there's a beginning, there's an end, it's one line, all you got to do is move the ball, da-da-da. But if you want the animal to do something really complicated and really interesting from the perspective of biology, the animal needs to be fully behaving, not just on a head post. Yeah, you move over while you talk on your phone. You do that. Keep talking on your phone. Keep reading your phone. Still reading and talking on her phone. She's still reading and talking on her phone. So the limitations of virtual reality are somewhat overcome by this paper. What they have done is created a Jamiroquai video type floor, and that floor moves X and Y underneath the animal. And then the rotation of the animal, which direction the head is facing, is done by head fixing the animal on a bearing drawn slide. So that when the animal applies a little pressure to the table it's on, or that pressure translates to pressure in the bearing that is holding the head fixed. And then a small motor makes sure that that pressure always stays around zero, so that the animal can walk around in the room, because the room moves underneath him, X and Y, and the animal can turn its head in any way it wants to, because the motor attached to the bearing that holds his head still is on a feedback loop, so that whenever he applies pressure, it counteracts it. So what you get is an animal that can explore an open field with two chambers, and he can basically walk around in any direction he wants to. So that is spectacular. And so what this paper does then is try to employ this methodology in a convenient cortical location where it is known that multiple streams of independent information come in. Where did they choose? They choose retrosplenial cortex, because retrosplenial cortex is kind of a higher order navigating body cortex. There's head direction there. There's other stuff in retrosplenial cortex too, but a lot of head direction goes to retrosplenial cortex. And since head direction is a very specific signal, then they thought, why not look at these neurons in the retrosplenial cortex and see if we can see head direction signals in the dendrites or in the soma, and whether or not these calcium signals line up or not, are coincident all the time or not. And so, it sounds like a pretty straightforward paper, but getting an apparatus to have natural head direction while still having the animal head fixed was a pretty serious methodological trick that they pulled off here. You can imagine lots of ways to do this, but none of them have imaging involved. Once you put the imaging in, you need a clever idea like this one. And I'm afraid this is like one of the more clever ideas, clever solutions for this problem. And I think, unless I'm mistaken, this methodology will be adapted by more labs simply because it's just too good. It's so clever. And if you see the video of the animals moving, one of the things that really sticks in my head as important is that in this type of a three-dimensional maze, number one, you could make it so that there are landmarks on the edge of the maze, colors or lights or whatever, so that there would be real landmarks like any other open field. And the second thing is you could put objects in here. Objects which could be inspected or whatever. So there's lots of stuff. You know, you could put a novel object in here. He's not even going to look at me. He's not even going to look. Because you don't give a shit. And that makes it pretty spectacular. So I'll just run down the figures really quick. I believe figure 1 is just the setup of the recording and how it works. And it shows the fact that they can get the XY position of the mouse. They can also have the head direction at all times. And then it shows the basic gist of how the bearing feedback works with the pressure on the head. Figure 2 is some real data. And I think figure 3 is where they look at head direction and show that head direction information is preserved in the cells they record from, whether they're in the open field or whether they're head fixed in this apparatus. Another extremely cool piece of data that comes from this paper. And now, I don't know if head direction cells like this fire in virtual reality. That's something that this paper seems to suggest that doesn't happen by showing you that they preserve the head direction information. But I'm not sure that that's not also present in virtual reality. But suffice it to say that potentially head direction could be a much stronger signal in this physical environment. And certainly the lack of statistical difference between the apparatus and open field it's an awesome observation. And then figure 4, they're just going to look at dendritic and somatic calcium signals in this two-compartment maze and see what proportion of those signals are coincident in dendrite and soma, what portion is just in dendrite, what portion is just in soma, and what do those signals look like. And so they show that the dendritic signal is sharper and faster than the somatic signal, at least on average. I mean, it's just a great advance. I mean, the dendritic thing is more or less showing what we already suspected. I guess I'm much more curious about the idea of cells with many dendrites. I mean, if a pyramidal cell has an apical dendrite separate from the soma, we still don't really have a good explanation for why. Especially if they can do their own calculations, but the soma ultimately is who has to signal, right? So that's weird. That was a no turn signal. Right turn. But what a fun paper. I mean, really, what a fun paper. They should be very proud. I think a lot of people have been trying to think about this problem for a while now. But this is the best solution I've seen so far. And I like it a lot better than virtual reality. Because again, the physical interaction with the environment is preserved. And that's really what experience is. And if you're not going to preserve that part of it, then you're making a bunch of assumptions about the experience that the animal has in virtual reality. And I don't think all of those are safe assumptions. Certainly we need to test them. I'd be very interested to see if in virtual reality they get direction cells, head direction cells in any of the systems underlying navigation. I'd be very curious as to what those cells do in virtual reality. There could already be a paper, I just don't know it. Hey, thanks for joining me on my ride. Excuse me, I'm doing something over here. Excuse me, I'm doing something. Thanks for joining me on my ride. That was a paper from Mark Harnett's lab showing that you can image dendrites and soma at the same time using a unique apparatus where the animal can spin its head relative to the two-photon scope, and then underneath the environment itself translates underneath the animal to essentially give us what virtual reality was trying to do, but now with a real reality. It's more like a Jamiroquai video, which makes it possible to have head direction in an apparatus like this. It's not clear to me whether it's been shown that in virtual reality we don't have head direction or the head direction signal is somehow compromised, but it wouldn't surprise me if it was. And this paper shows that statistically speaking, with this apparatus, head direction signal is the same open field or in this setup. I think it's a really great advance in terms of methodology, in terms of imaging neurons, and in terms of thinking about how neurons signal. I think it opens a lot of can of worms, though, and many cans of worms, in the sense of trying to think again now about if this is the way that pyramidal cells are working, that they have an apical dendrite which functions somewhat separately from the soma. How do we figure this into our models of learning? What information comes into layer one that would, number one, maybe warrant its own plasticity mechanism separate from the soma? And number two, how does this really, what implications does this have in terms of organizing inputs on the dendrite? So for example, are there dendrites that receive specific streams of input, and then other dendrites, maybe basal dendrites, receive completely disparate opposite inputs, and so the integration really occurs at the soma? Or does head direction really come in all dendrites, and we're just looking at two compartments which are signaling? So understanding what these two compartments do, we're still far away from. But Mark Harnett's lab has given us first a methodology with which we can better image animals in terms of their natural performance and their natural experience. And number two, has given us the first real taste of data showing that the apical dendrite and the soma can function separately as two, let's say, signaling units. Let's not call them computational units yet, but it looked like the activity in the dendrite and the soma was largely independent, or at least could be, depending on the inputs. So thanks for watching. Thanks for joining. If you like and subscribe, and I'll see you next time on JC on a Bike.